Okay, let's look at a few more examples of probability density functions, and while we're at it, some of these reference a cumulative distribution function. So how are they related? Well, cumulative, it's kind of in the title, means the sum up to that point, right? Like the accumulation. If I have a couple things happening here, and then, as we go, I have more and more probability, then the cumulative, I put on a graph here, as we go, right, the accumulation is increasing, and at the end we should get 1, because all probabilities, right, if we sum all probabilities of a certain event, we get 1. Now, because the cumulative is adding them up at each point, then really it's the integral, right, of this graph, the area one, the probability density function. When I integrate, I find the area under the curve, which yields me the cumulative. And then when we integrate, we do have this constant of variation. We'll look at that with some examples, right? We do have a plus c. We got to figure that out as well. Okay. So this first one doesn't necessarily talk about the cumulative, but we'll take a look as we go here. So this flashlight lasts somewhere between 30 hours and 50 hours, right? According to this, the density function is 1/20th. So find the probability the battery selected at random will last at least 35 hours. Well, if it lasts at least 35 hours, then what we're asking is 35 up to 50, right? Because that's the interval given, of the f of x, 120 dx. And integrate this, it's just a constant, so we get 1/20th x from 35 to 50, and therefore 1/20th multiplied by 50 minus 35, or 15/20, which is 3/4. And probability, right, usually we talk about probability as a percent, 75%. So the probability some random flashlight selected will last more than 35 hours, 75%. I want to do a quick sketch here, okay? 1/20th is just a horizontal line, and we have the interval from 30 to 50. Right, 1/20th. So the probability at each of these is always 1/20th. So that is our PDF, our probability density function. But the cumulative, as we go from 30 to 50, right, we know the accumulation of these is getting larger and larger and larger until we hit 1. Okay, so that's how these two are related, which will make better sense as we look at a few more examples. Okay, this next example, the cumulative distribution function for the random variable is given here. So notice most books have this capital F, which means they had done the antiderivative, right? So that is the antiderivative of some function. I have the cumulative. If I want to go backwards, right, then I need to do derivative. Going from a PDF to a CDF, I'm doing integral. So to go backwards, I'm doing derivative. And even if there was some constant we don't know, right, when we do derivative, that's 0. So this, the density function, I just need to find the derivative of the cumulative distribution function. So I need the derivative of the 1/2. The derivative of 1/2 square root, so I'm going to change it to x minus 1 to the 1/2 power. I need that derivative. So bring down the 1/2, we get 1/2 times 1/2 is 1/4, x minus 1 to the negative 1/2. So the corresponding density function is if I rewrote that 1 over 4 square root x minus 1. Okay. That is it. Or, you know, could have probably just left it like that, but either way. All right, the next one, now we're finding the cumulative distribution function given this density function. So now we are, in fact, doing integral. Okay. To get the cumulative, I'll just call it the CDF, we need to integrate f of x. So integrate that function given, 1/2 3 minus x, 3 minus x dx. All right, I think we should just distribute, so 3/2 minus 1/2 x dx. And that integral is 3/2 x minus 1/2 x squared over 2, and then plus some constant that we don't know. So how do we get that? Well, if we're talking a cumulative distribution, then this very left endpoint should be 0, right? If I substitute this in for x, I should get 0. Why? Because let's look at the previous question, the graph, right? The sum of all the probabilities of the very first point is 0 because remember you can't add area of a line, right? If I'm at f of x at 0, I get 0. And this x here, the end, we should get 1 because now we've summed all the probabilities. Well, I prefer using the 0 more, but either one is fine. So what does that mean? So this we're going to call f, capital F of x, right? We did the antiderivative. So if I substitute 1 in for x, I should get 0. So 3/2 times 1 minus 1/4 1 squared plus c, I don't know, we get 0. I should have given myself a bit more room, but that's okay. So we get 3/2 minus 1/4 plus c equals 0. And that's 5. This here, the sum is 6/4 minus 5/4. So c is negative 5/4. And therefore, just substitute that into this function, right? And we have it. I'll scroll over a tad. So therefore, the cumulative, which we're going to denote capital F, is 3/2 x minus 1/4 x squared minus 5/4. Alrighty. Last example, the time in minutes required to complete a certain subassembly is a random variable x with density function f of x 1/21 over x 1 over 21 x squared from 1 to 4. Okay, and that's in minutes. Use f of x to compute the probability that x is between 2 and 3. So what's the probability that, this assembly happens between 2 and 3 minutes? Taking out the outliers, I guess. So A, we're using f of x, so from 2 to 3, right? The integral of f of x, the probability density function, is equivalent to this. So we get 1 over 21 x to the third over 3 from 2 to 3, which means 1 over 63, 3 cubed minus 2 to the third, so that's 27 minus 8 is 19 over 63. Whatever that is a percent, right? Put that in a calculator and get my probability. But for math class, we're just going to go ahead and leave it. That's an exact answer. 19/63 is the probability. Okay, let's change colors to differentiate. So B, find the corresponding cumulative distribution function. Okay, well, looking ahead, we're doing this, and then we're going to use the result from B to compute the same probability we did in A. So we should get the same answer here. Ultimately, why I wanted to review this or do this example is to show you, like, when we are integrating the probability density function, we're technically finding the cumulative distribution function without really stating that's what we did. So how is that? Well, if I integrate 1 over 21x squared to get the cumulative, right, capital F, then I get this result that we got right here. I get 1 over 63 x to the third plus c, right? I don't know this constant. But then I'm going to use the endpoint, so not the 2 and 3, because that's probability we computed. When you look back at the original problem, it's distributed among 1 to 4, right? That's our probability density function. So therefore, if I plug in 1, I know I will get 0, right? It's the left endpoint. Or you could plug in 4, and you get 1. So therefore, if I plug in 1 into this function, 1/63, 1 to the third, plus c, we get 0. So that would mean c is negative 1 over 63. So our end result, let's go back to red, we get f of x equals 1/63 x to the third minus 1/63. Okay, and C, switch colors one more time. So C is saying use this result that we just got to compute the same probability. Well, that means we need f of 3 minus f of 2. So f of 3 would yield 1/63, and we could actually rewrite this. Let's go ahead and do that first. I'm going to factor out the 1/63. It's an ugly fraction. So we get 1/63 x cubed minus 1. All right. So now let's substitute 3 and 2. Change colors one more time. So f of 3, I'll do that in this color. F of 3. That's 1/63 times 3 to the third minus 1. Okay, minus green, how about that? So minus f of 2. Okay, that's 1/63, 2 to the third minus 1. You could kind of see it, like, look at this result here from A. That's really what we just did, right? I mean, we'll wrap it up, but you'll notice we're going to get the same result. So 8 minus 1 is 7, so minus 7 over 63. And over here we have 27 minus 1, so that's 26 over 63, which we get 19 over 63, and it is the same. Now, how was I saying it's the same? Well, if you notice, we have the 1/63 factored out, right? I could have factored it out here and here. And then if you look at the -1, if I distributed 1/63 to negative times -1, and I did the same here, right, they would cancel because this one's a negative 1/63, this one is a positive 1/63. So those would be gone. Then all I have left is this 3 to the third and this 2 to the third. Why is it minus? Again, this minus right here, right? So there it is. 3 to the third minus 2 to the third with the 1/63 factored out. Essentially, we are doing the same thing. We just never really found the cumulative distribution function in part A.